Welcome back everyone. So we've looked at heaps and why they may make a good choice for priority queue, but we haven't perhaps looked at their exact implementation yet. So let's have a further look at heaps and how we might implement them and understand them better. Let's have a look. So objectives of these two lectures or lessons is to understand a simple implementation of heaps, to be able to reason about the complexity of its operations, to be able to implement them and modify them, and to consider a particular application, for example, sorting a priority queue. To understand a cleverer construction method for heaps, bottom-up heap construction, and to understand heap sort, a fast recursive alternative to merge sort and quick sort. So if we remember as a bit of a recap, remember when we're basic of heaps that we wanted to make sure that they were complete, so that is they are filled from the bottom, and they were also in the correct order, so they're in the heap sort order, right? So that means that every node is greater than its children, right? So complete and heap ordered. Okay, so if we look at heaps versus, say, binary search trees, if we were to add items to a heap, these list of items, if we're inserting into an empty heap, we'd insert 5 straight away. Then obviously in the next position to its left, it would be inserted to there, and obviously we'd just enforce that it's also in the correct order, which it is, and then we would add 10, and then we would find, even though it's complete, it's not in the correct order, so we would have to rise that up to make sure it was in its correct order. So if we're now inserting -3 in the correct position, but it's in the correct, in the wrong order, so that means we have to rise -3 up until it's in its correct position, which is there. So let's look at the next item, 13. If we see 13 is again in the wrong order, so it needs to rise up and rise up again. So it goes into the root node. 20, obviously we need to raise 20 up twice again, so that goes into the root node. Insert the next item, 25. Again, we're going to need to rise up again, so that's in its correct position. And finally, 1. So 1 only needs to go up to there, so now that it is in its correct position. So it's complete and in the correct order. Let's have a look at a binary search tree. Remember, with a binary search tree, we don't necessarily have to have it balanced, but we need to have the invariant that everything on the left is less than the root and everything on the right is greater than the root. So let's have a look. So if we insert -7, that would just go to the left. If we're inserting 10, that would go to the right. So -3 would go left, but then it would have to go right because it's greater than -7. Alright, what about 13? Well, 13 will go right and right. What about 20? Well, 20 again will be a new maximum, and then 25 would be the new maximum, so it would just go down the right side, and 1 should go left, right, and then right again. So it would go into that position. So we can see, comparing it back to its heap, that it's very different, right? Because this is obviously unbalanced and they have different characteristics. So obviously in the heap, in the fact that it keeps the fact that it's complete, in the fact that it fills each level, it means that we can always ensure that either accessing items or potentially inserting can be done quite quickly, and perhaps quicker than maybe the depth of what we might find in a binary search tree. So let's look at an actual implementation for the priority queue, in this example a heap implementation. So how can we implement this data type? With a binary tree made of linked nodes. So like we did before, we could have a binary search tree and you have links. The downside, it's complex, requires extra pointers to move up the tree when we need to rise, so you're not just going down, you would need to know the parent as well, which means we require a lot of memory. However, if we did it with an array, it's possible thanks to completeness. And it's very compact. Let's explain what we mean by completeness and why it's so easy. Let's have a look at the order in which we add the elements. So we add 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. So that follows a complete binary tree if we're just to refer each of the nodes. What are the children of each node? Well, it's pretty easy to see that these are the children. So you got multiplied by 2 plus 1, etc. as you're going down. Obviously, as you're going up, you divide by 2, right? And the parent of each node is just half. So this representation is very useful by staying at 1 rather than 0 because it's easy to know what the children are and easy to know what the parent is. So let's have a look at an example. So this figure shows both the binary tree and the array equivalent. We'll highlight in grey each parent, so inner nodes with their children. Okay, so if we look at the position, if we were to start at element 0, index 0 I should say, with our array implementation, then the left child would be 1 and the right child would be 2. Right, so that would be their positions in the array, right? This would be a position 1, position 2 down here. Then if we look at the next one, we can see this would be the parent, and then you would have 3 and 4 being the left and right child. Again, if we were to look at this level, then we can see 3 would be 7 and 8, which is 7 and 8 here, or 8 and 9. And then the last one only really has a left child, so 5 we'd have to look at index 9 to actually access the element, which is 10 in this case. So we can see it's a little bit tricky to work out the left child and right child by using this notation, right? It is sort of multiplied by 2 plus 1 and multiplied by 2 plus 2, but that's not straightforward. And you can see similar sort of problem when we have the division as well. I mean, you probably could round down going up doing interdivision, but it's a little bit messy. Okay, so if we shift by 1, it will clarify the positions. So if we did this and just left the index 0 empty, and then we just start from index 1 to obviously up to n, the number of nodes that we want to store, or the number of elements, then this is a lot cleaner. So let's look at the example now. So if we look at the parent's position 1, to get the left child, you just multiply by 2, and then to get the right child, you just multiply by 2 and add 1. So therefore 2 multiplied by 2 is 4, multiplied by 2 plus 1 is 5. So it becomes a lot easier to access the child elements this way. And then like we said, for this one, it just has the left child, doesn't have a right child. So obviously we need to be a little bit careful when we get into a situation like this, that if we're trying to access the right child, we need to make sure it's less than the length of the array itself. So again, like I said, if you're accessing k, all it is 2 multiplied by k. Pretty straightforward. Whereas if we're accessing the right child, if it exists, you're doing 2 multiplied by k plus 1. So that's a lot cleaner to refer to it that way, and the only disadvantage is that we're wasting one element here, but it makes the mathematics a lot simpler. So if we consider each level, like just in summary, root at position 1, children of k is 2 times k and 2k plus 1 if they exist, and the parent of k is k divided by 2 using integer division, except for the root, obviously, because they don't have any parents. Okay, so let's look at a concrete implementation of the heap itself. So this is going to be pretty similar to our list ADT. The idea is now we're going to use an array to represent the heap. So we're going to have a minimum capacity like we did with the list ADT. And then we're going to pass it the maximum size. So now the main difference when we're keeping track of the length, remember we're staying at index 1, so we're now actually, the length is actually pointing to the last element rather than the next empty cell. And when we're doing the maximum, we just take the value passed plus the minimum capacity and we add 1 because obviously we're again accounting for that empty cell again. So now we need to add an extra cell in the array. If our heap has 10 elements, that would mean that we would have 11 slots in the array. Or 11 cells, however you want to refer to it. If we look at length, we just return length to get the length of the array. Pretty straightforward. And if full, well, that's again straightforward. We just need to check if the length plus 1 is the length here is equal to the capacity of the entire array itself. So that's it for this video. We've covered an introduction on how we might implement the heap ADT itself, and in this case we've used an array implementation because it just makes it a little bit neater with memory, and it allows us to easily access the parent and child nodes of a particular node if we need to rise or sink. In the next video we're going to look at how we might do an add operation on a heap using the array implementation. We'll see you then.